Hi guys, so we've finished our static stability module and we introduced this idea of stability derivatives, which are we presented them both in dimensional form. For example, if we're looking at the rate of change of rolling moments with roll rate, that would be the rolling moment is L and the roll rate is P, so that the derivative would be LP. If we were looking at in terms of the non-dimensional derivative, it would be CLP with a curly L. And if it's the non-dimensional derivative with respect to the non-dimensional rate, it would be CLP bar. So we introduced this and we looked at them a little bit to understand the relationship between these derivatives and aircraft motion. Some of these are really easy to think about in terms of their first order behavior. So the pitch stiffness, i.e. CM alpha, the pitch stiffness is the tendency of the aircraft to return to a level pitch attitude if disturbed. So some of them are easy to think about in those terms, and we also thought about some of the cross couplings and how we can think about those. So the tendency of the aircraft to roll when it yaws is given by the derivative CLR. I have to think in my head each time I do it. CLR. So we can sort of think about those derivatives and how they're going to affect aircraft motion, but we can't really go any further at looking into those derivatives, well, firstly those derivatives and how they affect motion, without understanding the entire aircraft equations of motion. Because once we have those, we'll understand the relationship between the forces and the moments and the motion of our aircraft, both in translational and rotational terms. Sorry, I can hear my dog scrambling around doing something very annoying in the background. Okay. So let's go ahead with this next module. So just before that, let's just talk about these stability derivatives a little bit. Okay, so for example, we had CM alpha, the rate of change of the pitching moment coefficient with the aerodynamic angle of attack, and then we look at CL, say for example CLR. Or R bar. This is the rate of change of the rolling moments with the yaw rate. So these derivatives are so important. Okay, I'm not just highlighting these two here, I'm highlighting these and all of the other derivatives we have. We're going to end up formulating a set of derivatives that actually goes up to 108, and that's what we're going to be developing in this module and the next one. We can have many more derivatives in this if we wanted to, because we're going to be looking at constraining ourselves to the 6 aircraft degrees of freedom, so that's X, Y, and Z motion, and pitch, yaw, and roll. And then we're going to look at the just 3 main control surfaces. So I've got my ailerons, my elevator, I'm actually missing one half of my elevator, and the rudder. So with those derivatives and those degrees of freedom, we end up with 108 stability derivatives. We could have many, many more. We could look at the second time derivative of a lot of these terms, and we'll talk more about this as we actually produce them. But where we get to, or the point that I want to make, is these stability derivatives, so not just these but all other derivatives, when we actually get them and when we determine them, these are just going to be numbers. And in fact, you'll be able to look these up for different sorts of aircraft and use them with the equations of motion and with the different formulations, both the non-linear and the linear equations of motion. You guys will be able to determine the stability characteristics of different types of aircraft. They're so important because these dictate the aircraft or how it wants to fly, its tendency to do things and its long-term behavior in flight. I've put it here, I've phrased that rather clumsily. Determine the way the aircraft will fly in a given situation, and what I mean by fly is respond to disturbances. And those disturbances can be, for example, external, and this could be e.g. gusts, or it could be control disturbances. So we could do a change to the control surfaces and just see how the aircraft actually responds. But I put here, they determine the way the aircraft will fly in a given situation, because I've put here that they are just some numbers. And we introduced how we could look at some examples of how we can determine them. So we went through looking at the roll damping. So we looked at roll damping was CLP. Okay, so we developed an estimate of CLP, and it was equal to the negative lift curve slope of the wing divided by 6. So we developed this numerical estimate. Now this is just an approximation for the actual roll damping of the aircraft. We looked at just the contribution of a rectangular wing, which my Spitfire here does not have. It has a beautiful elliptical shaped wing. There would be a contribution from the vertical and the horizontal stabilizer, and from the entire fuselage itself. So we could produce an estimate for this, but what I'm trying to get to in my roundabout way is saying that these estimates that we produced are just that, they are estimates, but furthermore, the stability derivatives are going to change depending on the trim state of the aircraft. And what do I mean by that? Change it depending on the trim state of the aircraft. Well, the aircraft's response is going to change. And remember that these stability derivatives are all just partial derivatives. So for example, if we were looking at the, say the weathercock stability, so we're looking at Cn beta. Cn beta, quotes weathercock. Okay, if we're looking at this derivative here, it's only going to be valid for the state at which we've calculated it or determined it. So if this was determined from, take for example, wind tunnel data, then this would be performed by putting the aircraft at different side slip angles and then measuring the yawing moments. And then we determine the derivative based upon those, and then we'd look at the linear relationship and come up with a number that gives us the rate of change of the yawing moment coefficient with the side slip. It's going to be a function of all sorts of things. It's also going to be, say, a function of alpha, Mach number. It's going to be a function of Reynolds number, which is not really what we care about in terms of the of what we're looking at for a given aircraft, but it will change maybe depending on the actual transit, the converting flight test data, or sorry, from wind tunnel data to full scale aircraft data. But fundamentally, it's going to be a function of all sorts of things. So a function of I put Mach number there. I should also put velocity as well. Okay, so it's going to be a function of all these things and many more. So what I mean is that these stability derivatives are only valid for the trim state at which they've been determined. Brackets and small disturbances therefrom. And we will get on to more of this as we go through Module 4 and we end up linearizing the equations of motion to look at the aircraft response. But I just want you guys to appreciate the significance of these numbers, the stability derivatives, and what they actually mean. So if you now go away and if you say Google the stability derivatives or the aerodynamic derivatives for a given aircraft, I'm challenging you guys to do this now. Okay, so on my course, go find some aerodynamic derivatives for aircraft you like and post them on the Slack site. Because what we're going to end up using later in this course, I want you guys to use the methodologies that we create to look at the stability of those aircraft. What you will find is that you can find these derivatives, but they'll also be defined at the state for which they're valid. So you'll say for a given aircraft, you'll see a set of derivatives for maybe landing, and a set of derivatives for cruise, set of derivatives for high power conditions as well, although landing could be one of those anyway. So what I'm saying is that you've got to just appreciate these numbers are only valid for the given flight state of the aircraft. And although we could look at some simple approximations here for, say, roll damping, to determine the actual full sets of derivatives, and there are many of them, we need to look at things like flight test data, wind tunnel data, flight test data, and look at higher order numerical techniques. So we would like to understand the relationship between the forces and the moments that we apply to the aircraft in general and the aircraft motion. And in order to do that, we need to develop the aircraft equations of motion, and we'll end up showing that these stability derivatives are what govern the aircraft response. So let's take module 3 now. We're going to work from a Newtonian framework and develop the full aircraft equations of motion. I say this is unconstrained aircraft flight. So to now describe unconstrained aircraft flight, we'll develop the aircraft's 6 degrees of freedom equations of motion. Unconstrained because in module 1, aircraft performance, we defined some equations that would help us understand steady level flight, and for that we constrained ourselves by setting lift equal to weight, thrust equal to drag, and unless we were looking at, say, loops, and we didn't even really look at any density variations in those, we would have set h dot is equal to 0. Now we're saying we're no longer making this true, so that's not true for us anymore. We're going to look at the relationship between the forces and the moments that we apply to the aircraft and the accelerations in both an axial sense and accelerations in a rotational sense. So let's go through that. Okay, so you should be comfortable with Newton's 3 laws. Newton's first law is an object remains in a state of uniform motion, so that can be in a state of rest or just not accelerating unless acted on by an external unbalanced force. Newton's second law is the force or the net force applied to an object is equal to the rate of change of momentum, and we're going to be using that one to help us develop things for this course. And the third one is for every action force there exists a reaction force that is equal in magnitude, opposite in direction, and by consequence is collinear. We're going to use Newton's second law to help us develop things, so we need to write this one down. And the formulation that we're going to use here, Newton's second law, we're going to say the sum of forces, which is a vector, is equal to m multiplied by a, which is also a vector, abs. Okay, so we're going to build up the left and the right hand side of this equation separately because it's maybe unclear yet how we're going to do that. Also, it's not maybe, of course it's unclear how we're going to do that, but it's maybe slightly more complex a problem than you might first appreciate. few reasons for this. So let's highlight the issues. So absolute acceleration. Okay, and what we're fundamentally going to show here, and what we're going to spend a lesson going over, is that the acceleration, for example, the absolute acceleration in the x direction is not simply equal to the time derivative of r, first that shouldn't be v, that should be u, of our velocity in that direction, okay? Because we've got other effects that occur because of aircraft rotation. We say due to Coriolis theorem. And you probably are going through very similar applications of this in spacecraft dynamics at the moment, and we're going to go through it in this course as well. Okay, so we need to work out how do we define absolute acceleration for our aircraft. Okay, so AABS, which is a vector, is going to be equal to the absolute acceleration in the A, Y, and Z. So we've got a vector to fit on this left-hand side. M is just the mass of the aircraft. Okay, so this one's probably the one that we're most comfortable with at the moment of all these terms. And then this force vector over here, well, we've got different parts to our force vector, but we know that our force vector, we defined it in, let's say we're using aircraft body axes, because we will use aircraft body axes. X, Y, and Z. Those are our components of force. But there are different things that go into this. So we know we've got, say, aerodynamic. We've got propulsive. And we've got gravitational. So we need to think about how we link all these forces together into the same frame of, so into the same axis system, such that we can combine all of these together and put them into here. Because at the moment, we haven't even defined them yet, but when we define them, we'll see that all three of these are defined in different axis systems, and we need to look at conversion to put them in here, to add them all together. So, in fact, let's do this first. Let's say this is our first problem. Okay, we're going to look at this one first, and then we're going to move on to looking at this. So these are our two problems that we need to solve in order to use. Once we've got them and we put our things into Newton's second law, we've got the aircraft equations of motion, and they're useful for us, okay? Those will give us the equations of motion for translation. We're then going to need to do the whole thing again using Newton's second law for rotation. Okay, so we're going to probably spend this first week just going over translation, and then we're going to go into rotation next week. Okay, so these are our two problems we're going to look at. How do we define all the forces in one axis set, and what on earth is absolute acceleration? Okay? So, let's speak about different axis sets that we've got. So we've already defined aircraft body axes. These are Okay, so if we have our aircraft, let's draw aircraft body axes on. So this is centered at the aircraft center of gravity. We have X direction sticking out through the front, Y sticks out along the starboard wing, and Z sticks down. There we've got forward, starboard, and down. Okay, or down in certain terms of our aircraft axes. So if our aircraft is climbing through vertically, then the Z direction is facing out this way now. So it's no longer just down in terms of the other axes. So we've got a person in there as well, just for good measure. So this is aircraft body axes, which we'd already defined. We're going to call this O, X, Y, Z. No, in fact, let's not call it O, X, Y, Z. Let's just say that we've got a position vector, R is equal to X, Y, and Z. Okay, so we don't have a subscript when we're working with aircraft body axes, because we're going to ultimately put all of the forces and the accelerations into these axes. Okay, and the reasons for this is because it helps us. So we measure velocities in aircraft body axes. So if we have a pitot-static probe here, that's where we measure things. We measure angular rates using rate gyroscopes on the aircraft as well. So everything's measured in aircraft body axes by virtue of the fact that that's the thing that we stick transducers to. So we measure quantities in body axes, so that's useful for us. We're going to put all of the other forces and the accelerations into aircraft body axes because that will help us out. Okay, and it's handy that we use body axes to develop our equations of motion because we don't have subscripts denoting which axis set we're in. It's probably more the other way around. We don't have the subscript on body axes because we use them to develop everything. This is our aircraft body axes and we're going to be using them. Let me just see if I... Okay, no, so let's talk about another axis set first. Let's talk about, let's cordon these off. Let's now talk about Earth axes. Okay, so in Earth axes, we all become flat earthers for the time being. And we assume the Earth is a flat plane. Okay, we obviously don't really believe it's a flat plane. I don't think anyone really believes the Earth is a flat plane. Everyone's just playing along with that stupid joke. But for the purpose of our Earth axes, we say we've got a big infinite plane upon which the aircraft takes off from. So if we define north going in that direction, east going in this direction, then our Earth axes have Z down, X is aligned with north, and then Y is defined going east. So because these are in Earth axes, we have to have a subscript E on each of these. So we say R E is equal to XE, YE, and ZE. Okay. It doesn't matter where 0 is in this axis set. We don't really care about that because what we're interested in is defining the relationship for how we orient our aircraft. Here's one more that we're going to use. There's two more we're going to talk about, one more we're going to use. We've got stability axes. I'll do my best to draw this one. So let's say, yeah, let's try and draw another aircraft. Okay, so our aircraft is flying along. Our stability plane is the plane that cuts the aircraft down its center. So then we look at the projection of the flight speed onto this. So let's draw, I've got my body axes, which are defined as X and Z, and we know these are body axes because I haven't got any subscripts. Stability are then, or is then just the projection of the flight speed in this plane. That's XS. ZS, and the angle that relates these two is alpha. Okay, it's very hard to draw this diagram in a 2D diagram. So what I've done, I've then drawn another diagram on the website. Let's just zoom in on this. Zoom in even more. Okay, so this is just related through alpha. So here we go. We can see we've got our aircraft body axes. We have a coincident y-axis, and we've got the green vectors here are aircraft stability axes. The blue ones are aircraft body axes. And along this axis here, if I get rid of stability, then we can see we've got a y sticking out in this direction as well. Okay, I've also put on here the flight speed. It's important to note that the stability axes don't take into account the side slip. Okay, or so it doesn't account for side slip because effectively we can't include them in these axes set. If we were to include side slip, we'd also look at wind axes. Wind axes are aligned with the oncoming vector, so VF. Okay, and then you can appreciate that from the diagram that we've got for stability on the website, we would align the other two components accordingly. It's a rotation around ZS. Okay. We're not actually going to use wind axes in this course. We're going to be using the other three. So we've got these different axes sets here, and let's think about different forces and how they're best defined. So when back in module 1, if we had our two-dimensional aircraft, then this might be the worst aircraft I've ever drawn here. But our two-dimensional aircraft, for the purposes of performance, we had lift, weight, drag, and thrust. And we separate these down. We said that these two are aerodynamic. This one is inertial. And this one is propulsive. Now, the actual definition of the aerodynamic forces is that these are defined normal to and parallel to the flight speed vector. And actually, more often than not, we find that we use the aerodynamic coefficients as defined in stability axes. So these are easiest to define in stability axes. Okay. Gravity is going to be easiest to define in Earth axes, because the only force that we've got in this reference frame is a force going down towards the center of the Earth. So in fact, we can write this now. Our sum of forces due to gravity in the Earth axis frame, 0, 0, mg. Okay, and remember G is 9.80665 meters per second squared for this course. Okay, for flight mechanics, this is the agreed upon value of gravitational acceleration. So we've got this here. Let's think about aerodynamic as well whilst we're here. Let's think about F aerodynamic in stability axes. Well, let's remind ourselves about stability axes. We've got, let's draw another aircraft. I'll try and not make it a terrible one. And let's give this a little bit more space, actually. Let's put this up here. So if we've got our oncoming flight speed vector, in fact, let's draw stability axes in red to be consistent. So I will draw on body axes. We're not actually going to use them, but let's just draw them on anyway, because it helps us remember the definition of stability. So this is our, that's actually our flight speed vector, or that would be VF cosine gamma really, but for our purpose we can just call it VF at the moment. Then what we have here is we've got X stability and Z stability. This here is alpha. So the forces we would have a lift in this direction and a drag in this direction. So actually our lift and our drag are both negative in stability axes. So our aerodynamic force in stability axes expressed as a vector is minus drag. We're going to say FAY minus lift. Okay, so we can just say what these parts are. And we'd actually also include any side force. So if we do have some side slip, we'll have a projection of our drag in the sideways plane that would give us this side force here. Okay, so we've got that one there, and let's think about propulsive as well. Propulsive, best defined in body axes. Okay, if we've got our aircraft here, draw our body axes on top of this, X and Y. Now we're going to say that we've got some form of thrust axis misalignment. So let's say we've got some thrust being produced down in this direction. Okay, and this is at some angle which we'll call theta t. Thrust axis inclination. Okay, so then our components of the propulsive force would be it would be FP as defined in body axes, so I don't need to put a subscript. This would then be thrust cosine theta t, no force in the y-axis. I think I drew that as a Z there, that was silly, or as a Y, that should be a Z. Okay, no force in the y-axis, and then in the direction that I've drawn positive Z in this, we'll say T sine theta T. Okay, we'll probably end up saying when we develop these equations of motion fully that we'll assume so we may just end up saying that theta is equal to 0 for this, but we'll see where we get with this course. Okay, so we've got these different forces. Just going back around here, we've got in Earth axes, we've got our gravitational force. In stability axes, we've got aerodynamic, and in body axes, we've got repulsive. And we want to add these all together, so ultimately they all need to be in body axes. So there's two conversions we need to determine. We need to look at the conversion between stability axes and body, and the conversion between Earth axes and body. So this one is much more complicated to do. So we're going to do it first, and then I'm going to leave you guys to develop this one, because it's just the same thing. I think I was trying to spell quantities there. I think I got lost midway through that word. We need to develop a means to define quantities, or convert quantities from Earth back and forth with body axes, okay? Because there's reasons why we're going to want to go between them both. So to develop the equations of motion, we need to be able to take our gravitational force and put it into body axes. But if, for example, we're looking at working out an aircraft's trajectory and plotting its displacement across the Earth, then we need to be able to convert the velocities, which we measure in body axes, and we'll end up showing from the equations of motion. We need to take those and then convert them into velocities on the Earth, okay, which would then be in Earth axes. So we need to develop a means to do this. Now, there's lots of different means that are used for this across aerospace, lots of different means that are used to perform this in different disciplines. So let's just list those types very quickly. Well, first, let's just talk about fundamentally what the problem is. So let's say I've got Earth, X, Y, and Z. And then I've got an aircraft somewhere in the world at some other arbitrary orientation. X, Y, and Z. So we need to be able to work out how the aircraft's orientation, which we already know is defined through the angles of the roll, pitch, and yaw angles, phi, theta, and psi, how that relates quantities that are defined in here to quantities here, and vice versa. Okay, so the aircraft's orientation is defined by its attitude and the three Euler angles. Okay, and the Euler angles are roll, which is phi, pitch, which is theta, and yaw, which is psi. So the way that we're going to convert in this course is by using something called the sequence of rotation, which is Euler angles. There's other means that we can do this. So to develop a transformation So this is the transformation between any vector in earth axes and any vector in body axes. Okay, the first one is the sequence of rotations. Second is we can end up using something called quaternion methods. And the last one is something called a direction cosine matrix. Now for fixed wing aerodynamics, we can use this one. Okay, this is the easier one to use. Easier to intuit, we'll say. Okay, because we end up with a 3x3 transformation matrix that gives us the relationship between these, between earth axes and body axes. These other two are slightly more complicated, so we'll say we won't explore. Every time that I sort of think I've got my head around quaternion methods, I have to relearn it any time I've got to use it. These tend to be used a little bit more in, certainly more in missile aerodynamics and in spacecraft. So just be aware that there are different ways to skin this cat, and the way that we're using is not the only way, but it is the way that we're going to use. So the sequence of rotations is what we're going to use. So we're going to determine 3 different transformation matrices for each of those angles. We're going to get one for yaw, one for pitch, one for roll, and then we're going to multiply them together, and that's going to produce a 3x3 transformation matrix, because each of those is 3x3s. It's going to help us convert between these two. Now the sequence that we must use for these, okay, we have to get the angles performed in the right angle. Is yaw is the first one, then pitch, then roll. Okay, you have to do it in this order, or otherwise it ain't correct. Okay, and what we'll end up seeing, the reason why it's not correct is because each angle actually defines a relationship between so firstly this yaw defines a relationship between earth axes and some intermediate axis set. Pitch then defines a relationship between that intermediate axis set and another intermediate axis set, and then roll defines that other intermediate axis set to earth axes, sorry, to body axes, So we're going to go through and develop these, and I'm going to go through the yaw Euler matrix first, and you guys are going to be left to look at how to do it for the other directions. How to get the rotation matrix. Now, this rotation matrices can be a bit of a bugger to get. Once you get your head around them, you should be fine, but they are taught somewhat confusingly. okay, and they can be taught somewhat confusingly. So I've included in the notes a really comprehensive definition of how to get this, and I'm going to go through a comprehensive means of working out this rotation first. So let's just go back up here again, and one of the reasons why I'm so hot on getting this to you guys is that I went back through my undergraduate notes, because I was always a little bit confused by Euler rotations, and then I looked back through my undergraduate notes, and some of the handouts I was given were actually incorrect, because these can be done a correct way or an incorrect way. Okay, so let's do them the proper way, and let's just remember how these are defined. Yaw is psi, which is about z. Pitch is theta, which is about y, and roll is phi, which is about x. Again, I've been careful, even though I've not put subscripts on there. Let's say this is z body y1 and x2, and that will become a little bit more meaningful once we actually get to those. So how to get the rotation matrix. So we know that ultimately what we're looking for is R in our body axes is going to be equal to sum total transformation matrix, total rotation matrix, multiplied by some quantity in earth axes. And we're going to produce 3 rotation matrices. So we're going to say it's going to be equal to T3, which is a function of the roll angle, multiplied by T2, which is a function of theta, multiplied by T1, which is a function of psi, multiplied by RE. Okay, so producing each of these is going to be relatively simple, I hope, and we're going to work out how to produce these. So it's just the same procedure performed 3 times to get each one of these. Again, then it's a bunch of matrix multiplication to get our big expanded matrix. Okay, so we're going to define them in this order, and we're going to get this one first. So our first rotation is through psi around about z earth to get the first rotation matrix. So the way that we draw this, the way to get started is think about the axes that you're starting with. And our first axis that we're starting with is earth axes. And if it's going around z, then we've got to have the other 2 axes have got to be x and y. Okay, so we draw, the first step is to draw our unrotated axes on here. X pointing forward, y pointing the other way. So I've got xe. And I've got YE here, and this defines my earth axes. This is the unrotated. Okay, now we know that a positive rotation for here, if we use the right hand screw rule, okay, this is the wrong hand for the video, so let's do it here with my hand that I can't quite make a fist with. If I put my thumb into the page, which would be that way, then I can't even do it on screen, it would be that way, wouldn't it? Then so by the right hand screw rule, fingers would curl around in this direction. So a positive rotation is going to be in this direction. Okay, positive rotation there. So we then draw our rotated axis sets on here. And the angle that we've gone through is psi. So this takes us to x1, y1, which is an intermediate axis set. Okay, so first step's done. Okay, if you've got a right-handed axis set, which is what you need to have, so make sure that you've got so the way that I got the rotation here is using the right hand rule. So x is up, y is to the right, z has to point into the middle of the page, or has to point into the screen rather, by accordance with the right hand rule. I then put my right thumb along that, twisted my fingers around, that gives me a clockwise rotation. So that's the definition of a positive rotation in yaw. Okay, so I've got this here. We then say we treat the unrotated direction as being the hypotenuse of a right-angled triangle. So I then say, okay, well, my triangle here is going to be, let's draw this on in red. Got one there, and I've got one here. Okay, so we're going to look at the different components of this triangle that I've got now, and I'll draw these on in red. Let's draw it on here. So I say that component would be xe cosine psi, and then this component is in this direction, and this is xe sine psi. Similarly up here I've got ye sine psi, and I've then got ye cosine psi. Okay, make sure you get the correct direction, and just remember that you're treating the original direction as the hypotenuse of a triangle, or we can think about we're trying to represent, if we have a new quantity, what it would be equal to in the old axis set. So we've got this here, and I'll just even draw on the right angle there, just to show you that's our right angle triangle that we're looking at. So what we're then going to do is we're then going to collect components along our new axes. Okay, so let's say, again, you wouldn't necessarily draw such a complicated, all of this writing around a diagram. I'd like to see you drawing these out when you derive them, but the narration is really just because I'm teaching. So we'll say, let's make these green. So what's along x1? So we're going to look for components that are parallel to x1 now. So we've got, well, x1's in this direction. So we've got xe cosine psi and ye sine psi, and they're both pointed in the same direction as x1. So we can say x1 is equal to xe cosine psi plus ye sine psi. Okay, let's do the same with, let's pick another color. Let's do the same with now what's along y1. I'm deliberately not using fantastic language to talk about these because I want you guys to think about them in the sense that you're actually doing them. So now I'm thinking, what is in the same direction as y1? Okay, so y1 is going down this direction. So I've got ye cosine psi, which is positive, and I've got xe sine psi, which is going in the other direction. So I can write these down. I say y1 is equal to ye cosine psi minus xe sine psi. Make it a little bit smaller so you can see it. And then if we were to draw the other component of both of these, well, both of them would just be straight into the page. We'd have our z would be into the page and z would be into the page in both of them. So lastly, we would have z1 is equal to ze in this case. So we can write these all out, collecting these, bringing them down. We say x1 is equal to xe cosine psi plus ye sine psi plus nothing times ze. y1 is equal to minus xe sine psi plus ye cosine psi plus nothing times ze, and then ze is equal to xe multiplied by nothing plus ye multiplied by nothing plus ze. And I've messed up there because I wrote ze, that should have been z1, sorry. Okay, this might seem like a funny way to be writing it out, but the reason I'm writing it out is because we want to get a matrix from this. So we could just say here x1, y1 and z1 is equal to Okay, so this is then our first transformation matrix. So we've got R1 is equal to this transformation matrix multiplied by RE. So we've taken this matrix here, or we've made this matrix here, and this converts quantities from Earth axes into our first intermediate axis set. So we're 1/3 of the way there. And most importantly, we've now learned how to do an Euler transform, which you might have had to do in other courses. But if you don't do them this way, you can get a little bit confused. Okay, well, you might have been taught how to do them in slightly other different means as well. I don't mind as long as you end up with the right answer here. Okay, and also I've been doing this long enough that I can see what it's going to be and I can do a shortcut. But sometimes you might kid yourself, you understand them, and you'll end up with the wrong answer. Okay, so just make sure you know what you're doing. You will always have. Well, first I can see this is incorrect, because that should not be a sine there, that should be a cosine. You guys are probably screaming at your computers. I say screaming at your computers, I understand no one's really that invested in this. Okay, but when we look at these, you'll always notice that we're always going to have the cosine terms that are the sort of direct terms, if you wish. So x is always going to be cosine of x, y is always going to be cosine of y, and z, well, in this case, is a 1. So you'll either have a 1 or a cosine in those direct terms. You'll always have one negative term, and it's always going to be a sine term that's negative, and sines give us these sort of couplings. So y is a sine of x, x is a sine of y in this example. Okay, so let's do one more, and I'm going to sort of rush through this a little bit. So let's go through, do our second rotation. Second rotation is the pitch one. So that's our first rotation. Let's box this off. So we're going from our intermediate axis set 1 to some other intermediate axis set through pitch. And then pitch is defined about the y1. Okay, so y1 is this, actually is not the same as Earth y, nor the same as body y in this case. It's an intermediate axis set. So again, we do the same thing. I'm going to use my right hand. So I'm going to think about the easiest way of drawing this. I like to draw my axes with my aircraft flying from left to right. So I have a tendency to draw them like this. And what colors did I use here? I used blue for my intermediate. So let's keep that consistent. Let's say I'm going to draw X and Z. Okay, so my unrotated axis set is my intermediate 1 in this case. So if this is my axis set, then the direction of positive rotation, so that's X, Z, so Y is pointing into the page. Wrap my thumb around Y, it's going to be a clockwise rotation again. So let's make our new axes green. X2 and Y2. Okay, and I'm just going to write the components in now. I might even fast forward through this in the video, we'll see. That shouldn't be a Z, that should be a Y. Sorry, it shouldn't be a Y, it should be a Z. Okay, so I'm collecting components. I see I've got x1 cosine theta, and I've got minus z1 sine theta. And then in the z direction, I've got z2, I've got x1 sine theta. I know it's going to be cosine, it's going to be positive anyway, but I'm just going to go through that. So it'll be z1 cosine theta. And then I know that my y2 is just going to be the same as y1 because that's the axis about which we rotated. So I can see immediately that my transformation matrix, so T2 in this case, is going to be equal to, well, y is the one that's the same, so I have a 1 in the middle, and then, well, x, I've got cosine theta, 0, minus sine theta, 0, 0, and then in z, I've got sine theta, 0, cosine theta. Okay, and we'll just do a quick check this makes sense. Well, I've got cosines in my diagonal, cosines are 1s in my diagonal. I've got 2 other sine terms and only one of them is negative. So that's a matrix that makes sense in accordance with the rules that we set up a moment ago. And we know that what we've just created is any vector in our new second intermediate axis set is equal to our transformation matrix multiplied by some vector in our first intermediate axis set. So it's therefore equal to T2 multiplied by T1 multiplied by something in our Earth axis set. Okay, so we've done our second one here. I always tend to get bigger as I go on down the page. I never seem to find myself getting smaller here. But let's just do our last one. I'm going to do this as quickly as I can. Well, not as quickly as I can that you guys can follow, I think. Because hopefully you've got the understanding of what these Euler rotations are. So third and last, we're going to say that this is rotation in the roll angle. So this is from R2 to our body axes through the Euler roll angle. That's about x2. Okay, so if it's about x2, I think I'm going to have my y-axis. So let's just remember the colors I had. Green was my x2 in this case. So here I'm drawing y2, z2. So x is pointing into the page. Rotation is again clockwise. Let's pick another color I haven't used just to define our body axes. So now what we have y and z, and we've got our roll here now. So y sine phi, z sine phi. You actually only really need to draw the sines just to get yourself around the directions, because you know the cosines are always going to be positive. So we can see immediately here that y is equal to y2 cosine phi plus z2 sine phi, and z is equal to z2 cosine phi minus y2 sine phi. Okay, so our transformation matrix is going to be T3 is equal to, well, x is the constant term in here because x is simply equal to x2. It's going to be 1. And then the terms we've just produced are going to go into the lower right hand side of this matrix. So y is cosine sine. And then it's minus sine here. Okay, so that's all of our transformation matrices produced. And just remember that what we've just produced, we now say that a quantity in body axes is equal to transformation matrix 3 multiplied by something in our second intermediate axis set. So it's therefore equal to T3, T2, T1 defined by something in Earth axes. So we've got these 3 axis sets now, okay? And I'm not going to make you guys do the algebraic multiplication in an examination. I used to do that. I don't necessarily see the worth in doing this now, because I'm not giving you guys a big formal exam for sort of your midterm on this. You would have done this in the previous course. But if you take these matrices and you multiply them together, I'll probably fast forward through this. So let's say we've got T, this is our total transformation, is equal to T3, T2, T1. And let's just, in fact, let's just copy this in because I don't want to spend time doing this. There we go. So that is our total transformation matrix. And what this enables us to do is take quantities from one axis and put them into the other. Okay, we're actually, we're going to use this quite a bit in this course, and we're going to use it for later parts to convert between, say, quantities like the velocities in body axes. We're going to use them to convert between that and Earth axes. We're going to use it mainly to convert the gravity vector, or the gravitational force. So we can use it in this format to convert, remember, so something in body axes is equal to this matrix above multiplied by something in Earth axes. If you want to go the other way around, RE is going to be equal to the inverse of this matrix multiplied by something in body axes. Now, handily, T is orthogonal. So T inverse is just equal to the transpose of this matrix, which is really handy for us. Okay, I'm not going to write out the transpose or copy and paste it because you guys can just get that. Okay, so now that we've got this, we can use it. We can use it to take our gravity vector, or the gravitational force vector, and put it into body axes. So what we're going to end up saying is that F gravity in body axes is going to be equal to transformation matrix multiplied by F G defined in Earth axes. And remember that our F G in Earth was equal to 0, 0 mg. Okay, so let's do that. Let's do that multiplication. And again, I'm just going to copy this in because it's easier to do. So you should be able to see here, actually, the only terms we need are in this last column, because all we're going to get 3 components of the gravitational force vector. We don't need any of these first few bits, which is really handy for us. Okay, it's handy for doing a complicated matrix multiplication. So what we end up with, the first term is going to be minus sine theta multiplied by mg. The second term is going to be sine phi cosine theta multiplied by mg, and the last one is going to be cosine phi cosine theta multiplied by mg. Okay, so what we now have our gravitational force in body axes. So let's look back at what we were trying to do. Here we go. So we had forces that we wanted to convert in. No, let's go back to here. Was it here? Yes, okay. So we had forces, this one here, we've now converted this one into body axes. Okay, so we've done that. We still need to do the same with the aerodynamic forces. We need to convert those from stability axes into body axes. So we now need to convert from stability to body. So let's just remember our definition of these axes. We've got X here, Y here, and let's draw XS, YS, and this is rotated through angle alpha. There's a tendency for me to want to, because I'm recording this and I know I can go over my time allowance to do everything for you and give you all this extra material. But I think it would be better if you guys did this rotation on your own. So go through and do this rotation. What you're going to end up showing is that a quantity in body axes is equal to, now it's rotation about, I've been stupid, I've drawn Y there, that should very clearly be Z, sorry. So it should be a rotation about Y. So we're expecting this one in the middle to be 1. We should have cosine alpha 0 minus sine alpha 0, 0, sine alpha 0, cosine alpha. That's our rotation matrix to go from stability axes into body axes. And remember the forces that we've got that we care about. We're trying to take the aerodynamic forces and stability. So we've got FAS, which is again the force vector because of aerodynamic forces in stability axes is going to be equal to minus drag FAY minus lift, and that's transposed. So our vector, when you do the multiplication, we end up showing that the aerodynamic force vector is equal to minus D cos alpha plus L sine alpha. FAY doesn't move, which is useful, minus D sine alpha minus L cosine alpha. Okay, so we've now got all of our components in the correct axes set. Okay, so we can add them all together and put them into the left-hand side of our equation. These give us our forces. So let's write these down. So remember, we were looking for the sum of forces, which we defined in body axes. We don't normally have a subscript B for body, but sometimes it's there just to show you no ambiguity. Multiplied by MA abs. So we still don't know what to do with this right-hand side, but we're pretty good with the left now. So this left-hand side is going to be force due to gravitational in body, plus the force due to aerodynamic in body, plus the force due to propulsion in body. Again, subscript isn't normally put for B, but it's there just to show you that we've got the that we're absolutely unambiguously in body axes at this moment. So this is now going to be the sum of forces in body axes, and if we take all the components that we had before, so the first one is that that gravitational force. So that's just going to be minus mg sine theta, mg sine phi cosine theta, mg cosine phi cosine theta. Okay, so that's our gravitational. Our aerodynamic then becomes, well, we've just, let me copy these over because we're doing a, nope. I've just got them up here, so let's just copy them. put a plus sign there. And then the propulsive is the last one that we've got in here. So we've got plus, I should have another plus there and another plus there, plus t cosine theta t, whatever that theta t is that we end up using. I'll include Fty there, which we haven't actually included before, but that's any component of the propulsive force or the thrust acting in the y direction, plus t sine theta t. I think I use a slightly different, I use the opposite sign convention for theta t in the notes, but it doesn't really matter because it's just arbitrary. And we're ultimately going to end up showing that it's different, that we're going to set it equal to 0 anyway in the end, but it's there just for completeness. So what we've done, we've built up this left-hand side of these equations. This is the forces that give us the, effectively, these provide the translational accelerations in aircraft flight. So we've built up the left-hand side of these equations. We are going to work at building up the right-hand side next. So we've built up the left-hand side. We're going to build up the right-hand side next. So I'm going to take a break here, edit this video, and then I'll record the next one, which goes through the right-hand side. Slightly more complicated in the way that we've got to work out whatever this absolute acceleration is. But once we've got those, you guys should be pretty good for this week, I think. Okay, so thanks for listening. I'll see you all